cells. So electrochemistry is what the title of our unit is. I call it redox chemistry, but the actual unit is called electrochemistry. And it's converting chemical energy into electrical energy. So when we were doing the redox portion, we were just looking at the reactions and the chemistry behind it. Now we're going to start looking at the electric potential in there. Okay? A voltaic cell is when there is a spontaneous redox reaction. Voltaic is when there is a spontaneous redox reaction. What has to happen for a spontaneous redox reaction to happen? The oxidizing agent has to be higher than the reducing agent. Okay? A voltaic cell uses a spontaneous chemical redox reaction to produce an electric current flow. So we can take like a meter, a voltmeter, and we can measure the amount of electricity of a spontaneous reaction. So when we looked at page 7, there's all those voltages on the side page. That's going to start where we're going. Okay, we're going to look at the electricity part of it. We're going to draw a diagram, and it's going to take this entire space with words and pictures, okay, of what a voltaic cell has. There's 2 pieces to a voltaic cell. Beaker 1 and beaker 2. Okay, these are just strictly beakers. In order for this to happen, we need to connect them. So we're going to connect them with what we call a salt bridge. This is a salt bridge. Okay. And then we're going to introduce 2 typically metals. And we're going to connect them with electrical wires to a voltmeter. Okay, so that's a voltmeter. Now we've got these, and we call them electrodes, because metal does what with electricity? Conducts electricity. Okay, so these are our electrodes. What we're going to do is we're going to fill them with a solution. Okay, and let's make this solution, I'm just going to write it over here. Zinc sulfate. So what's going to be floating around in here but zinc ions, right? And sulfate ions. Because it's going to dissociate, right? This metal electrode then, we're going to make this zinc. Oops, sorry. I moved it and you couldn't see it. We're going to make this metal electrode zinc. Let's look over here then, and let's say that this solution is copper sulfate. What can we say about the sulfate ion between these 2 things? They're what, Declan? Yep. Okay, So they're just hanging out there. The sulfate ions are just spectator ions. So in here, we're going to have copper 2 plus ions floating around. And we're going to have sulfate ions floating around. Sulfate ions are not interfering with the reaction though, right? Because they're spectator ions. A voltmeter measures the current. Measures or detects current. And the unit is going to be volts. There is a positive and a negative end to the electrode or to the voltmeter. They got a black and a red end. And in this salt bridge is a solution that does not interfere with the reaction. It allows the electrolytes to move forwards and backwards. So typically, something that does not interfere with any reaction is something that is a spectator ion. And what is one of the ones we talk about lots in Chem 20? What is a spectator ion that we often see? Starts with an N and it ends with an nitrate. Nitrate. And we need to build it with a salt. Sodium. Okay, in this particular case, we typically use potassium. So potassium nitrate is in this salt bridge, and it's plugged off here. Those ones there aren't plugged off because we want the movement of ions, but we don't want to lose all of the potassium nitrate out of the salt bridge. All right, when we look at this here, this line here, and we're going to draw on some physics 30 knowledge, and here's a positive. Which way is my flow of electrons? Negative to positive. So my electrons are going to flow this way. Okay? It's going to repel through. Okay, remember what we said? We said that Voltaic cell is a spontaneous reaction. When we look on page 7, which is the higher, Declan? Yeah, but it does flow this way because we want them to be attracted to this electrode. We got it. We're good. What has to happen for this to be a spontaneous reaction between Okay, so then that means that zinc 2 plus is going to be the strong, or zinc solid is going to be the strong reducing agent, and this is going to be the oxidation half reaction. Okay, so this is the oxidation half reaction. And what does it look like? How do we write that formula? How do we, okay. Now what about copper as the reduction half reaction? Again, referring back to page 7. How do I write and show that this is a reduction in oxidation numbers? Okay. This means then that the zinc solid, the zinc metal, is the anode. Okay. It decomposes. So this piece of metal strip, if I had zinc solution on one side and copper solution on the other side, and we let that go, eventually that zinc metal that's in the beaker would be completely broken down if we had enough solution and enough time. Because it's an anode, it's going to oxidize and it's going to break down. It's going to go from a zinc metal to a zinc ion. That's what our reaction says is going to happen. Okay? Zinc 2 plus concentration then is going to what? Increase or decrease? Okay. Let's look at the copper anode or copper electrode. This is copper 2 plus. So the copper solid is happening at what we call the cathode. Remember what we said about anions and cations? Anions is a negative ion and cathode is C, a positive ion. That still lends itself to this piece. So we're going to see copper 2 plus ions reduce, right, or decrease in concentration, because that's what it says. Copper 2 plus is eventually going to go and build copper solid. And the copper strip okay, the copper strip is going to build up. Yep. Going to build up. I'm gonna leave it there. We're gonna like bend your mind a little bit. So we're gonna add a statement to this, but let's just go through the stuff first. Let's look at the definitions. Okay, there's lots of components. So we looked at the anode. So the anode is where the oxidation occurs. Electrons are leaving the anode. A cathode is where the reduction occurs, so electrons flow into the cathode. They're usually metal conductors that electrons carry in and out of. An electrolyte is the solution that contains ions that are typically going to be spectator ions. There is an external current. This is this piece here. Okay? This wire here is what we call our external current. Those are the alligator clips that I attach that are attached to wires which are attached to the voltmeter. And then there's a salt bridge. It's a U-shaped tube that has an electrolytic solution, which means it has a salt solution because metals conduct electricity, that allow ions to flow between the two beakers to maintain a charged balance, but keeps each half reaction separate. So it can't be something that, like, we couldn't put copper sulfate in there because copper is going to interfere with the reaction. Nitrate doesn't interfere with the reaction. And if we look, I think potassium is one of the last ones. Typically, it doesn't interfere with the reaction. This is what you need to take away. The metal that acts as a cathode will be found in the half cell that has the strongest oxidizing agent. Highlight that loud. The cathode has the strongest oxidizing agent. Okay. The metal that acts as the anode will be found in the one that has the strongest reducing agent. And this ensures that the redox reaction will happen. If we didn't, the reaction would stop. It wouldn't go forward. It would need help. That's how this happens. It has to be spontaneous. So when we look back at our diagram here, we said that the oxidation half reaction was this because zinc metal was the strongest reducing agent. So zinc is the strongest reducing agent. It's found at the anode. Okay? And so zinc solid is the anode. Copper 2 plus, so these are the ions floating around in the solution, are the strongest oxidizing agents. That's what you identified from table or page 7. Because the oxidizing agent has to be higher than the reducing agent for it to be a spontaneous reaction. We're going to find this at the cathode, which means that copper solid is the cathode. So there's lots of different things that you need to pay attention to now. Now we're going to totally utilize that table on page 7. You got to be familiar with reading it. Oxidizing agents get stronger as they work from the top to the bottom. Reducing agents are strong at the bottom up to the top. Okay? There's another way that we can do it, that cell. We don't have to use a salt bridge. Declan, if you look in that tall, skinny cupboard on the right-hand side, you'll find between solutions in order to maintain a charge balance, but it keeps the bulk of the solutions forming. So instead of having 2 beakers, with a salt bridge in between and 2 electrodes, now you just put this porcelain cup inside of 1 beaker and you create your electrical current. So that's all we've done. This porous cup here just replaces 1 beaker. Replaces 1 beaker and the salt bridge. Okay? So I showed you what that looks like. Let's look at how this actually works. There's a specific way now to write this picture out. This whole entire picture, we can write it with the ion symbols. So like zinc solid, zinc 2 plus, copper solid, copper 2 plus. We can write it out in chemistry language. We're always going to start with the anode on the left. So it's the negative guy. Then we put this line and we write our electrolyte. And then we draw the salt bridge. So 2 lines indicate the salt bridge. And then we write the next electrolyte. And then we write the cathode, which is the positive.
So the salt bridge is just shown by 2 lines?
2 lines. Yeah, we don't write anything in. We just show that there's a salt bridge. And so this is what we call cell notation. Same thing. You have two separate things happening. And so the cup, the porcelain cup, would be these two lines. So the anode has which reaction? Which redox reaction? Is it the oxidation half reaction or the reduction half reaction? And the cathode is then going to be the okay. So this just shows that there's anion movement from the salt bridge. And this is cation movement. Okay, that just shows that there's movement through the salt bridge. All right, so what was the oxidation half reaction again? Yeah. And what was the reduction half reaction? Copper solid. Okay, so cell notation. The anode is going to be the metal. So we're going to write zinc solid. The electrolyte, the ions floating around in the solution. The ions floating around in the solution. Going to be zinc 2 plus. There's a salt bridge, whether it's an actual salt bridge or a porous cup, there's still movement of ions. And then on the other side over here, we have copper ions in the solution. And then our electrode is copper solid. Okay? Sometimes you will see it written like this, where they actually include the spectator ions. Okay? Okay, here's an example. It says identify the anode and cathode for the Voltaic cell. Write out the individual half reactions that occur at each electrode and write out the overall redox reaction that takes place. This is a proton exchange membrane fuel cell. So I don't know if you can see this, but these are hydrogen gas molecules. Can you see that better? H2. These are H plus ions in the middle. And on this side, this is oxygen. Okay, it shows that the electrons are flowing this way. This is the reactant, this is reactant, hydrogen in, oxygen in. This is the membrane in between. So this is porous carbon right here and porous carbon. So now we don't have two like zinc and copper metal sticks. Now we have two carbon rods. So if this is a voltaic cell, it has to be spontaneous, right? Okay, so we have hydrogen ions and we have oxygen. Of those two, looking at table 7, which one is your strongest reducing agent? We've got hydrogen, hydrogen ions, oxygen, hydrogen ions, and water. Those are our options. Look at your table and you tell me, what is your strongest oxidizing agent and what is your strongest reducing agent? There is water. Yep, right here. There's water there. In here? Here. Here? Oh, right here. These are hydrogens. Here, here, and here. This is hydrogen here. Okay. What did you guys decide? What are the half reactions that we're going to take? So this is going to be your cathode. Okay. Now it says that we should also write out the overall reaction. How do I do that? Balance out your electrons. How do I do that? The hydrogens are going to cancel out, right? The electrons are going to cancel out. So a proton exchange membrane produces water. Okay, let's look at an alkaline fuel cell. I can't see. Can you guys see what they produce? Yeah, I know. I got a water there and an electron there. I'm just wondering what. Oh, it's electrons? Oh, yeah, I see.
On both sides, it's
Okay. All right. So this is a voltaic cell. So it must be Spontaneous, which means what? The OA is higher than the RA. So what is the OA and what is the RA? What's going to be my overall? How do I go from two half reactions to an overall reaction? Times the bottom one by 2 to balance out your electrons. I see that I have water here, so my waters are going to cancel out, my electrons are going to cancel out, and so I'm going to be left with, and my hydroxides are going to cancel out. Hang on, I got to be left with something. This should have been a 2. Hang on.
You should have two.
2 waters. That's where I made my mistake. It's going to give me, this is going to cross out and leave me with 2. Okay. It doesn't balance? Yeah, it does. 2 oxygens, 2 oxygens, 2 hydrogen. Oh, I just need a 2 here because I forgot my 2 there. Okay. So which one of these is going to be my cathode? Mm-hmm. Are we sure?
No,
The reduction half reaction is on the cathode side. So you were right. Have confidence in yourselves. The oxidation half reaction occurs at the anode. Okay? Okay, in theory, we can get through this. All right, inert electrodes. Voltaic cells that have half reactions that don't involve a metal. So we just looked at 2. One had oxygen and the other one had hydrogen or a hydroxide or a water. Okay, if they don't involve a metal, you have to give it an inert electrode. And so an inert electrode is made up of a material that doesn't react with the reactants or create a product in a redox reaction, but allows everything to flow. Most common types of inert electrodes are platinum and carbon. So if we were to look at this particular reaction here, lead plus iron 3 chloride gives us iron 2 chloride and lead chloride. We need to go all the way down to cell notation with this. First things first, what are the oxidation numbers? So what's changing? Lead is, which means that it is what kind of agent is it? It's a reducing agent. This is reducing. So iron is your oxidizing agent. So my oxidation half reaction is going to be lead solid and my reduction half reaction is going to be iron 3 plus 1 electron. It's going to go to iron 2 plus. Okay. What do we see in this particular reaction? There's no metal. So we're going to have to use an inert electrode. There's no metal here. We went iron 3 plus to iron 2 plus. There is no metal produced here. But this is an ion. This is in solution. It's not a solid. There's no metal solid. There's no electrode that's part of this equation. So when we do cell notation, we go anode, electrolyte, salt bridge, electrolyte, cathode. Always. Never changes. Doesn't matter what we're doing, it never changes. Okay? Our anode is going to be, which reaction happens at the anode? Oxidation. So we're going to go lead solid. What's my electrolyte? Cl is a spectator ion. Lead 2 plus. My salt bridge or my porous cup. My electrolyte here. Yep. And iron 3 plus. We're going to have both of those in solution. And because I have no metal, let's use platinum as a solid. This is an inert electrode. Platinum or carbon? Which is cheaper? Carbon. Okay? We will not be cutting off catalytic converters to get the platinum electrode out of vehicles to supply the chem lab. Just saying. We're going to go with the carbon electrodes. Okay? Let's look at this. Half reaction. I'll write it quick. I'm going to leave this for you for homework. Make sure you write this down because this is your homework assignment. I don't want this second H here. Just write it down, Declan. There. Okay, this is your homework. Write the half reactions and draw the diagram.